The last strategy that I'm going to talk about is called multiple imputation. And this is really what we should do. The problem is that in most projects, you're missing a little bit of data and you have to decide how much time to spend on the missing data and dealing with it as opposed to the rest of your goals for the analysis. Now, the rest of your goals for the analysis might never work at all if you don't deal with the missingness in some way. But you don't have to every time do the fanciest thing, especially when you are a student. But I do want you to be aware of multiple imputation, which is the best strategy out there. It's called MI. Okay. So number one, these are the steps. Choose a strategy for randomly imputing missing values. So it's going to be some version of what I just showed you for strategy 5. Like you decide on some non-parametric or parametric model that you can use to randomly draw a missing value, or randomly draw an imputed value for each place where a value is missing in a way that depends on the other variables. So you're going to choose a strategy, okay? Then you're going to use that strategy to create a filled-in data set. Then you're going to repeat this previous step to create M filled in data sets. So you randomly fill in the values once, put that data set aside, go back to the version that has blanks in it. Use the same strategy but with a different seed. Randomly fill in the values again. Keep going, M times. Now, when this method was first proposed, computers were not as fast and popular and common as they are now. So there's some papers showing that you could do this 5 or 10 times and achieve reasonable results. But now there's no reason not to create maybe 1,000 filled-in data sets. What we're trying to do is understand the uncertainty. So let me pause and think about the motivation for using this approach that I'm not finished describing, rather than one of the ones we had previously. So first we thought, again, to summarize, first we thought about creating a missingness category. That works great. We thought about just dropping the missing values. That's going to lead to bias. So then we have to fill in a number. We thought about imputing the mean. That maintains the mean, but you underestimate the variance. We thought about imputing by drawing from that variable's observed distribution. Now we've maintained the variance, but we've lost the relationship between variables. So then we thought about drawing from a parametric or a non-parametric model that connects this variable that has missingness to other variables, and now we're doing much better. We're maintaining the relationship. But here's the problem that we're trying to solve with this multiple imputation technique. If you fill in the missing values one time and then hand that data set off to your collaborator and say, here's the data set we're going to use, you are then assuming that the values you imputed are correct, right? But they're not. You know that you filled them in by randomly drawing, and that if you randomly drew again, you get different values. So if you fill in the values exactly once and use that data set as the only data set you're going to analyze, you are underestimating the uncertainty in your final answers, because you're ignoring the fact that you filled in a 14 for somebody's education, but it just as easily could have been a 15. And you're ignoring that because you're pretending that the values you imputed are actually correct. So what multiple imputation is trying to do is say, hey, let's find a way to summarize how much the answers would have ranged over a range of possible different ways I could have filled in the blanks in the data set. And that's how we get to the step 3. So now we have M data sets, like 1,000 different data sets that are identical on the observed values, but have all different values that I've imputed for the missing ones. Here's what you do. For step 4, we run the analysis, whatever the analysis you have planned. You run the analysis separately for each data set. So maybe you're trying to estimate some slope parameters. Now you have 1,000 different estimates of that slope parameter, right? So you do this and it leads to M estimates of your estimand. Whatever your plan is for estimating your estimand, now you've done it M times. You have 1,000 different values. Your overall estimate of your estimand is the mean of these m separate values. So the overall estimate you report of the m separate estimates but you also need a standard error. In other words, you need to be able to create a confidence interval. You need to measure the variance. So the standard error of your overall estimate for the estimand is based on a formula that I'm not going to put up here. Estimate for the estimand. I'm not going to put the formula up here. Rather, I'm going to say that the standard error of the overall estimate for the estimand reflects two things. The standard error for each estimate and the variance of the m estimates. So think about what we're doing here, right? You have something like, data set number 1, right? So m's numbered 1. And data set number 1, your estimate, say we're trying to estimate some kind of slope coefficient, right? Maybe it's equal to 5, okay? And then you also have a standard error for that thing. So maybe let me put it this way, like an S with a little beta 1 hat on it, right? What is the square root of the estimated variance of this thing? Maybe you get like 1.2. Then you have another data set. This is data set number 2. Maybe this time your estimate is 4, and the standard error of that thing is 1.7. Then you have data set number 3, and this time you get a 4.9, and the standard error is 1.5, et cetera, et cetera. Okay, so we already said that your overall estimate of the estimand is just going to be the mean of all these numbers. But now suppose you want to come up with a confidence interval for that thing, right? That overall mean. So what we're saying is the confidence interval you calculate is going to be overall estimate plus or minus 2 times a standard error that is a function of each of these individual standard errors. That's the standard error for each estimate. Each of your m estimates comes with its own standard error, like how variable is your slope estimate within each different data set. So we're going to include those. We're going to take the average of those. But then also, what is the variance of these 1,000 different estimates of the slope? How much do the data sets deviate from each other? Okay, so the standard error for each estimate is about the uncertainty in your estimates just from your one data set that you've imputed. And then when I say the variance of the m estimates, that's the uncertainty that's due to the missing data, because for each of the m different data sets, you've imputed different values. And so they're not all going to be the same. The variance of the m estimates is going to reflect to what extent your guess at your estimand changes based on how you imputed the missing data. So what I'm saying here is the overall answer that you provide after multiple imputation is the average of your 1,000 different estimates from 1,000 different imputed data sets. And to get a confidence interval for that thing, you do a calculation that reflects both how much variability you think there was within each of your imputed data sets and how much the different imputed data sets vary from each other.